Okay. Uh. Gonna do a model here and with the intent to make sense of the idea of composite functions. So let's say we got lots of critters reproduce quickly. Okay. Now, the rate at which they reproduce when the food concentration is C, okay, their growth rate is Kc. Now, we haven't yet developed the mathematical model for compound interest, but everybody should know that by the time they're 12 years old. Okay. And maybe 14, because maybe not everybody's brain is grown enough at 12 years old to do that. But I had a lot of smart friends, and we all understood it by the time we were 12. Who had little bank accounts. Okay, so that's the model. Okay, well, it follows from this model that if P of T is a population function, one possible model for the population is P of T equals P naught, where P naught is the initial population. So what I say is think of a fish tank with little tiny fish like guppies. Okay, I think most people know what guppies are. Let's say you put a handful of guppies into a big tank and keep their food concentration to where they can get plenty to eat. Okay. Then before they get too crowded, and then this is an oversimplified model. We can change it a little bit. We can refine it. That's what we do with models, but let's just keep it really simple. Let's just say that the only thing that affects is food concentration. The only thing that affects their reproductive rate is food concentration. Then you have this model, and we'll talk about compound interest and see how this kind of a model can make a lot of sense. Typically, let's say that Kc, whatever K is, whatever C is, let's say that Kc was 4%, which is 0.04. Then you'd have like 1.04 raised to the T power. Okay, so Kc is just going to give you a decimal representing a percent. And this means that every time T increases by 1, let's say maybe T is measured in days. Okay, so every day your population is going to increase by 4%. Okay, well, that means it'll double about every 18 days. So it's not going to take long before that tank is full. And there are too many guppies to actually follow this model because there isn't enough room for them to move around and get all the food they want, although that's a problem tonight. Okay. So a lot of things we can take into account of this model, but here's an oversimplified model. Now, let's say that C actually changes with time. Okay. There's plenty of food at the beginning, but after, let's say T's in days, after 30 days, the concentration of food is down to 0. So that's going to do bad things to the population if it goes this far. But let's just say that after, let's say 10 days, we feed them again. So we're just going to be interested in what happens for the first 10 days. So the domain of this function, well, we'll impose a domain in a minute. First thing is, I'm asking, can we find a formula for C of T, which is a straight line from here to here? Okay, now we might already have that because we talked about that a little bit earlier, and I just threw that out as a problem to work on while I summarize what we talked about previously. Okay, now everybody got that sort of, except for maybe the negative sign in front of the slope. C of T is a straight line, so we could say that's one right hand next to B, but in this case, our variable is T. So we're going to call that MT plus B. Slope is rise over run. Now we've done this. Okay, this is kind of review. And the rise is -15. Okay, so here's your rise. And here's your run. So that's -15 over 30, which is of course 1/2. Now B, I made it easy on you. I gave you y-intercept. Okay, the vertical intercept is 15. So C of T is look what I did, same thing you did. -1/2. So now we can replace C by this C of T function. Now I've got a notational problem here. It kind of obscures what's going on as the composite, so let me fix that. Okay, now I can't fix the notational problem, but I can say that we can now write T of T is P naught times 1 plus 15 minus 1/2 T raised to the T power. Now, unfortunately, this isn't really a composite function. When I started writing this model, I was going to do it with temperature instead of time. So I'm going to tinker with the model a little bit. We do this with models, you know, we cast around, we try something, we see if it makes sense, and then we refine it. And we're going to refine this model a couple of times. My first refinement is going to be I want the food concentration to change with the density of the population. So I'm going to go ahead and make that change, and then we'll pick it up on the video. Okay, I left K off here. It's K times 2. So we have this, and of course, this could be simplified. And it could look like this. Now, that's a challenging function to analyze. And it's not a particularly good model, and it doesn't quite illustrate what I wanted to illustrate, but it illustrates something important. Okay, so I'm not necessarily sorry I did that. We'll modify this in a minute. Okay, so again, we have this, and we understand that, well, C isn't just a constant number. Okay, we said that C changes with time, like we feed them, and then 10 days later, we come back and feed them again. Okay, so maybe the actual C of T function is piecewise function that looks like that. Okay, so piecewise linear function, and of course, each one of these functions is this one, but translated to the right 10 units, we means we replace T by T minus 10. We talked about those transformations. Okay, now that's something you're going to see quite a bit of in calculus. And now we're just preparing you for it, and you're totally prepared. We're just playing around with a few of the more subtle ideas, so you'll understand them even better when you get there. Okay. Now, I'm going to want this C, instead of varying with time, and it will vary with time, but we're going to make C not a function of time, but we're going to make it a function of the density of fish. Okay, so I'm going to make that modification, and then we'll talk about it. Okay, I'm going to let you think about this first, and I'll summarize. Okay, we're going to change gears a little bit on this, and we're going to focus on this rate. Okay, so if C is a function of critter density, we can do the same sort of thing. Okay, the concentration of food depends on the density. So let's just say that we have this graph. Density is going to be delta. That's just a Greek letter. And we use Greek letters when we run out of good letters to use in our alphabet. Okay. This is the Greek letter delta that evolved sort of into D. So that's just another letter. We just expanded our choice of letters. A lot of times we use D for density. I don't like that because of the way D is used in calculus. So I kind of avoid it. Whether that's a good idea in this case or not, I'm not doing calculus. I'm not going to get into that, but okay. There's our density letter. Here's C, which is a function of delta. Just like before, C was a function of time, C is a function of density. All right. We get the formula for C. We see that the slope is -3. Delta is 5 on this vertical line here, including at this point, this is where delta is 5. So our rise is 15 down to 0. Our run will go from 0 to 5. That's a slope of -15 over 3, which is -15 over 5, which is 3. So our mx plus b becomes m delta plus b. Our b is our intercept, which is 15, and our slope is -3. So there's our function C of delta equals this. So now when the concentration is C, let's say the rate is in some way a little more complicated than the rate we gave. It's no longer K times C, it's K times 10 plus C. The question then is, what's the rate as a function of delta? So let's see how we did on that. Okay, now the answer is kind of obvious, but since I didn't tell you what it's going to look like, it's very good that you were able to get it. And you kind of discovered the way function notation works, but you already know how function notation works. Okay, so now I'm going to do an intermediate step. Okay, if C is just a constant, then that's perfectly good for R of C. Okay. So there's our function rule. This is the rule for the function R. Okay, well, now C is in turn a function of delta. So we write R of C of delta. Well, R of C of delta, if we see that C has now been replaced by C of delta. So we replace C here by C of delta. And we understand function notation quite well. Pick that up very well. So I think we understand that we just follow this rule, replace C by C of delta. But of course, C of delta is, ever write it down? Yeah. -3 plus -3 delta plus 15. And of course, now we can add the 10 and the 15. And there we have it. Okay, so just an example of the mechanics of a compounded fund. That may be a little hard to understand why the concentration might be like this. Well, I just made it up. And it's reasonable because greater concentration gives you a greater rate of reproduction, a rate of growth. Now, this doesn't make a lot of sense if we let C of delta go all the way to 0, because this means C goes to 0, we still have a positive rate of growth. Okay, you would think if these guys ran out of food, then they wouldn't have the energy to lay the eggs or whatever they do. Okay, to produce the eggs. Okay, they wouldn't be producing as many, and the population would tend to tail off. So this is, well, we want to say that this applies as long as C of delta is greater than 8. Okay. So we put a domain restriction on this. The domain of this function now is C is greater than or equal to 8. Now, if C is greater than or equal to 8, what's your restriction on delta? Because now we want to do the rate as a function of delta density. So for C to be greater than 8, what do you have to say about delta? Okay, so we take this a little further. With restriction that C is greater than or equal to 8, well, if delta gets too big, C is going to be less than 8, right? So we just look at the graph and say, well, if this is 15, 8 would be maybe about here. We're going to put a green circle around this domain restriction. Okay. And in same color, I'll make a line where C equals 8. I probably didn't do a very good job of locating that line. But so be it. Okay. Well, C is greater than 8 on this line. So for this much of the curve, including this endpoint here, C is greater than or equal to 8. Well, what can you say about delta if C is greater than or equal to 8? Well, I'm going to let you see if you can state this. Okay, now, he said, well, you know, delta is going to be between here and here. Okay, so delta's got to be here. Okay, so delta is now restricted to this interval. Now, what's this interval? You can estimate it. According to my estimate, it looks like Okay, it looks like delta's maybe 3. Now, actually, y'all made the same estimate based on your graph. Now, I don't believe that for a minute. On your graph or my graph, okay? But that's an honest estimate, that is a little over halfway between 0 and 5. There's a whole number, but then rounded to 3, okay? Maybe it'd be 2.6, 2.7, but it clearly looks like it's more than halfway, but it can't be. Why can't it be? Because if you go from 0 to 15, 8 is more than halfway to 15. Okay. So the interval where C is less than 8 has to be bigger than the interval C is greater than 8. That makes sense? Yeah, this interval here is bigger than this interval. So this interval has to be smaller than this interval, but it doesn't look like it. Okay, but that's just because we both managed to draw bad graphs. And of course, I drew mine first, so you can blame me for that. All right. And really the problem is like horizontal axis kind of, for example, influences things. Okay, well, that's an estimate. That's a picture of what you need for delta. If C has to be greater than or equal to 8, and why is C greater than or equal to 8? Again, because it doesn't make any sense to let C get too big, because if you let the concentration go all the way to 0, you still have a positive rate here. Okay, and you don't expect growth to really continue when these guys run out of food. They're voracious. They're small before they eat, they can eat. Okay. All right. Well, can we figure out what the restriction on C really needs to be? Going to do this in a couple of ways. We're going to get to an algebraic way to do it. Here's again C versus delta. We can sketch a triangle here, and the dimensions of this triangle. Well, this side here is going to go from 8 up to 15. So this side is going to be 7. And we don't know what either of these other two sides are. But what we do know is that on the big triangle, and we've got 7 here. We don't know what we've got here. We don't know what we've got here either, but we really care about this. Okay, the little triangle, this is what we have. The big triangle has the same shape. It's geometrically similar to the little triangle, but you've got 15 here. And you've got 5 here. So that we'll call this seven, and we're going to call this delta max. The maximum value delta could have for C to still be greater than 8. And I can write we've got similar triangles and figure out what delta max has to be. Now I have to ask the question, did you do some work with similar triangles in your courses? Okay, so we did that very well. Okay. And you know, the response I got from most people, yeah, we did this, it's kind of vague. I think you set up the ratio and then proceeded to set up the right ratio and solve it correctly. Okay, so that's very good. Now I would set this off as delta max over 7 equals, well, let's say delta max is a side that corresponds to 5, so that ought to be 5. And 7 corresponds to the 15, so that would be 15. Okay. And then do what you want, but I just multiply both sides by 7. Okay. So that delta max goes there is 7 here, and you got the 5 over 15 here, and you get 35 over 15, which equals 7/3. And if you want to make sense of the number, you make a mixed number out of that. It's 2 1/3. Okay, 7/3 is okay, but 2 1/3, if you want to put that on the scale here, it's a little less than halfway. From 0 to 5, halfway would be 2 1/2, right? And 2 1/3 is a little bit less than 2 1/2. Okay, so we have determined that we have to restrict delta to the interval from 0 to 2 1/3 in order to restrict C to be greater than or equal to A. Okay, so by similar triangles, similar triangles are great. They imply that to have C greater or equal to A, delta has to be between 0 and 2 1/3. Now, there's another way to get this, and it's simply with inequality. Of course, you know, we could write this as an inequality. We could say 0 is less than or equal to delta, less than or equal to 2 1/3. Okay. We didn't have to use similar triangles. We could have set it like this. I'll do that algebraically. I'll even label it as such. See if delta has to be between 0 and 8. And why 0? Well, it can't be less than 0. We can't have a negative concentration of food. Okay. So we could write 0 less than or equal to right at 15 minus 3 delta less than or equal to 8. Okay, now what do you do to solve that inequality? Okay, now I did a bonehead thing here. But I haven't done that many bonehead things today, so I'm doing better than usual. I said C is between 0 and 8, right? And you got something that didn't make sense. You got delta could be 5, among other things, okay? Well, that's because this is the right inequality. C is between 8 and 15, not between 0 and 8. Okay? So let's fix this. We're going to put 8 here, and we're going to put 15 here. Now, there's still going to be a tendency to get a wrong answer because people that have done inequalities for a while tend to forget that when you multiply or divide both sides of an inequality by a negative, it switches the direction of the inequality. Okay, so we discovered that. So keeping in mind that with that one caveat, let's see what we get. Okay, now I'm just going to go ahead and do this, but you can just go ahead and work it while I'm explaining it. Let's go back to what I got. Okay, so first thing, to isolate delta here, what do we have to do? Well, we have to subtract 15, then we have to divide by -3. Okay. Now, this is really two inequalities. We could separately solve this inequality. Make sure you can see that. We can separately solve this inequality here. Doing that, we would subtract 15 from both sides and then divide by -3, but we'd have to reverse the inequality. And then we could do the same thing here. We take exactly the same steps. We subtract 15 from both sides and divide by -3. Well, let's just do that all at once. Let's just do both inequalities simultaneously. So we're going to get 8 minus 15 less than or equal to -3 delta, less than or equal to 15 minus 15. Okay. That's what we get when we subtract 15 from this, and this. And that gives us -7, less than or equal to -3 delta, less than or equal to 0. Then we divide by -3. And that's going to leave us delta. It's going to give us -7 over -3. It's going to give us 0 over -3. The inequality, though, has to reverse because we multiplied or divided in this case by the negative. And we get (7/3) greater than or equal to delta, greater than or equal to 0. And then if we write the inequality in the usual order with the smallest number first, we see 0 is less than or equal to delta. And that's less than or equal to 7/3. And that matches the inequality I wrote here based on the similar triangles. So as in mathematics, as in much of mathematics, most of mathematics, there's more than one route to the solution. And if you use 2 routes, it's a good way to check those routes. If they don't agree, that's when the fun starts. You learn something, okay, by fixing it. Okay, well, there we have it. So there's quite a bit about composites. Now, I'm not going to try to bring this back to the original model where the C went into the time, because it turns out that actually gives us a function of 2 variables. Those functions are important. C would be a function of both delta and time. But then, of course, if delta is a function of time, then it gets interesting. Now, that actually leads us into a much bigger topic, differential equations. Okay, if you take a good second semester of applied calculus, you're supposed to get some multivariable calculus and a little bit of differential equations. Okay. And that would be very valuable to you, depending where you go in biology. Okay, it's a much simplified multivariable calculus and differential equations, okay? You only spend a few weeks on the two topics, and engineers spend a whole year. And it's very, very challenging for them. In applied calculus, somebody of decent aptitude, and that's certainly the case here. It really isn't that bad. I love teaching that course. Back when I taught it 3 times a year, year round, along with several others. Okay, well, here we have. How does this fit into what we know about composite functions? Let's see what we plotted. We've got about 8 minutes left. I don't want to get us off and something's going to take longer than that. Okay, I'm just going to go back to the standard model that you can see in open math of bacteria growth on food. Okay. Here's a population growth function. We use capital C for temperature. Let's be specific. Let's let K be 0.03 times T minus 5. Okay, now it's understood. Make that 0.003. Okay. That T is measured in Celsius degrees. Okay. Let's go to Fahrenheit. Okay. That'll make sense. Okay. T minus 40. Now, why T minus 40? Is because bacteria start growing at about temperature 40. Temperature 40 or lower, bacteria pretty much don't grow. Okay, and they don't grow very fast at 40. That's not really a linear model. This is kind of a poor model, but it'll do for right now. Okay, well, that's again not a composite function. That kind of gives you well, now if temperature is changing, like you take this stuff out of the refrigerator, its temperature is going to start approaching room temperature. And then you could have a temperature function that's going to exponentially approach room temperature, which we'll say is 70 degrees. So T is going to be like 70 times 1 minus, oh, it's 2 to the base for my exponential. Now, remember, we know about the 2 to the x function. We can graph the 2 to the x function and so forth. So you kind of know how it's shaped. So let's say we do 1 minus 2 to the negative 0.01 T. If you know, if you graph that function, it looks like this. And actually, I don't have room to write a good book, but I'm going to squeeze it in there. I'm not going to explain how this graph comes about. I could if we had more time. But okay, now here's temperature. It starts at 40. Let's just say 40 is here. This is not very well drawn to scale. It's going to give you a curve that looks something like this. So here's how your temperature is changing. The change in temperature changes the rate at which your bacteria grows. And you can then substitute this temperature function in here for capital T. And there's an aspect of compounded functions in this model. But you ultimately end up with some kind of function T. Okay. So we saw last time a model. We're driving a car up the road. Okay. And the model involved how many miles we get per gallon at different speeds. And how do I put it? And a function that tells us our speed is a function of time. Okay, so we know the speed is a function of time, and the rate at which we're burning gas as a function of how many miles how fast we're traveling. We get that kind of a neat composite. A little hard to conceptualize that. I think maybe these models are a little easier to conceptualize. Gives you a feel. And something that's terribly missing, I think. So I'm going to write a whole series of application problems in these. It's fairly easy to do. In the open math, I only see one example. Anywhere, I can only find one example of an interpretation of composite function. I'm sure there are probably a couple of others, but they're that hard to find. There aren't many. It's not something that's done prominently. So we'll look more at this. Now, next time I propose that we look at compound interest. And it'll make it easier to understand some of why we used a model like this. Okay. It's a simpler model. But unless you have a better idea, that's what I'd like to do in Tuesday.